Imagine being trapped in a cosmic prison where the bars are made of light itself. The stars are calling, but they're screaming from impossible distances. Light takes 4 years just to reach our nearest neighbor. Our galaxy is 100,000 light years wide. You could live 1,000 lifetimes and never cross it. What if the question isn't how fast can we go, but can we change the distance itself? If you're fascinated by the cutting edge of space exploration, make sure to hit that subscribe button. Now let's begin. For decades, faster-than-light travel seemed like pure fantasy, something reserved for science fiction shows like Star Trek. The speed of light, roughly 299,792 kilometers per second, appeared to be an unbreakable cosmic speed limit set by Einstein's theory of special relativity. According to this theory, as an object with mass approaches light speed, it requires more and more energy to accelerate further. At exactly light speed, the energy requirement becomes infinite. It's a wall built into the fabric of reality itself. But here's where things get fascinating. Einstein's general theory of relativity, published in 1915, describes gravity not as a force but as the curvature of spacetime itself. Massive objects like stars and planets bend the fabric of space and time around them, creating what we experience as gravity. This insight opened a door that special relativity had seemingly closed. If space-time can be bent, curved, and warped by mass and energy, could we potentially manipulate it in ways that allow travel across vast distances without actually moving faster than light through space? This question lingered in the minds of physicists for generations. Then, in 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper that sent ripples through the scientific community. Working at the University of Wales, Alcubierre proposed a solution to Einstein's field equations that described what would later be called the Alcubierre drive or warp drive. His idea was elegant and mind-bending. Instead of pushing a spacecraft through space at impossible speeds, why not move space itself around the spacecraft? Imagine you're standing on a rubber sheet. Normally, to get from one side to the other, you'd have to walk across it. That's conventional travel. But what if you could grab the sheet in front of you and pull it toward yourself while simultaneously pushing the sheet behind you away? You'd move across the sheet without actually walking. Alcubierre's warp drive works on a similar principle. It would create a bubble of normal space-time around a spacecraft. In front of the bubble, space-time contracts, bringing your destination closer. Behind the bubble, space-time expands, pushing your starting point farther away. The spacecraft itself would sit comfortably inside the bubble, never actually accelerating or moving through space. Space would be moving around it, the mathematics checked out. Alcubierre showed that such a configuration doesn't violate general relativity. You wouldn't be traveling faster than light through space. You'd be riding a wave of space-time itself. Inside your warp bubble, you could sit back and sip coffee while the universe rearranged itself around you, carrying you to Alpha Centauri, the Orion Nebula, or even distant galaxies. But there was a catch, a massive one. To create this warp bubble, Alcubierre's calculations showed that you'd need something called exotic matter, specifically matter with negative mass or negative energy density. In our everyday experience, all matter has positive mass. A rock, a planet, a star all have positive mass that attracts other matter gravitationally. Negative mass would do the opposite, creating a kind of anti-gravity that repels normal matter. And here's the problem. We've never observed negative mass in nature. It might not even exist. Even if it did exist, the amounts required were astronomical. Early estimates suggested you'd need the negative mass energy equivalent of the entire planet Jupiter just to create a warp bubble large enough to carry a small spacecraft. Some calculations pushed the requirement even higher into multiple solar masses. These weren't just engineering challenges. They seemed like fundamental impossibilities. For years, the Alcubierre drive remained a beautiful mathematical curiosity, a proof that faster-than-light travel didn't technically violate physics, but also a stark reminder of how far we were from making it real. Scientists filed it away alongside other exotic concepts like traversable wormholes, interesting to think about but seemingly forever out of reach. Then something changed. In 2021, two researchers named Alexei Bobrik and Gianni Martire published a paper that challenged one of the fundamental assumptions about warp drives. They proposed a new way to classify warp drive spacetimes, and in doing so, they opened up possibilities that had been previously overlooked. Their work suggested that for certain types of warp bubbles, particularly those traveling slower than light, you might not need exotic negative energy at all. Instead, these subluminal warp drives could potentially work with positive energy, the kind of energy we actually understand and can manipulate. This was huge. It meant that warp drive technology might not require us to discover or create something that doesn't exist in known physics. It shifted the conversation from "this is impossible because we need unobtainium" to "this is incredibly difficult but might be achievable with known physics." But the story gets even more interesting. Just a few months ago, in December 2025, a physicist named Rodal published groundbreaking work that takes the field even further. Rodal derived the first fully explicit, continuous, analytical warp drive spacetime that is irrotational, meaning the warp field doesn't have any spinning or vortex-like motion. This matters because previous warp drive models, including Alcubierre's original design and another popular model called the Nacelle drive, had vorticity, a kind of rotational property in how space-time moves. Why does vorticity matter? Think of it like this. If you're creating a bubble in space-time, you want that bubble to be as smooth and stable as possible. Vorticity creates turbulence, instabilities, and dramatically increases the amount of exotic negative energy you need. Rodal's irrotational design is smoother, more stable, and requires far less exotic matter. How much less? The numbers are astonishing. Rodal's warp drive geometry shows a peak negative energy requirement that's roughly 38 times smaller than Alcubierre's original model, and an incredible 2,600 times smaller than the Nacelle drive. When physicists tested the null energy condition, which is one way to measure how much you're violating the normal rules of physics, Rodal's design showed violations more than 60 times smaller than the Nacelle model. But here's the truly remarkable part. When Rodal and colleagues calculated the overall energy balance, the net proper energy density across the entire warp bubble was consistent with 0 to 4 decimal places. Let me say that again. The total energy required might actually balance out to essentially nothing. This doesn't mean the warp drive requires no energy. Creating and maintaining the specific geometry still demands power, but it suggests that the exotic negative energy component could be far smaller than anyone previously thought. If you're captivated by these mind-bending concepts, I've created something special for you. It's called Mars in 15 Minutes, the No Telescope Observation Guide. This isn't just another e-book. It's your personal gateway to connecting with our neighboring world, using nothing but your own eyes and the night sky. Inside, you'll discover when and where to spot Mars throughout the year, how to identify it among the stars, and what those ancient wanderers saw when they looked up and called it the Red Planet. The link is right in the description below. These recent developments represent more than incremental progress. They signal a fundamental shift in how seriously the scientific community is taking warp drive physics. Just a few years ago, most physicists would have dismissed warp drive as interesting mathematics, but physically impossible. Today, major research institutions are publishing peer-reviewed papers exploring the details. Computational physicists have even developed specialized software tools like one called Warpax that can analyze the energy conditions of different warp drive geometries and tell us exactly how much they bend or break the known rules of physics. One research team led by Harold White, a physicist who previously worked at NASA's Johnson Space Center on advanced propulsion concepts, published work in December 2025 exploring what they call interior flat cylindrical nacelle warp bubbles. Instead of creating one continuous bubble of warped spacetime around a spacecraft, their design segments the exotic energy into discrete cylindrical channels, kind of like having multiple smaller warp generators arranged around your ship instead of one big one. This approach localizes the exotic stress energy into specific, manageable regions and creates a flat space-time region inside the bubble where passengers could travel comfortably, synchronized with time outside the bubble. Think about what that means. One of the weird consequences of Einstein's relativity is time dilation. When you travel at high speeds or in strong gravitational fields, time passes differently for you than for people in normal space. This could create all sorts of problems for space travelers. You might leave Earth, spend what feels like a few months traveling, and return to find decades or centuries have passed. White's interior flat design solves this by ensuring that clocks inside the warp bubble tick at the same rate as clocks outside. You wouldn't lose time. Your journey to another star system wouldn't cost you your connection to everyone you left behind. But let's be absolutely clear about where we stand. These are theoretical advances, brilliant and important, but still very much on paper. We haven't built anything. We haven't created a warp bubble in a laboratory. We haven't even definitively proven that the exotic matter these designs require actually exists in nature. The challenges remaining are enormous. First, there's still the exotic matter problem. Even though newer designs like Rodal's require vastly less negative energy than earlier models, they still require some. Where do we get it? Some physicists point to the Casimir effect, a quantum phenomenon where two metal plates placed extremely close together in a vacuum experience an attractive force. This happens because the space between the plates has slightly less quantum energy than the space outside, creating a kind of negative energy region. It's real, we've measured it, but the amounts are incredibly tiny. Scaling this up to create a warp bubble would require technologies we can barely imagine. Second, even if we had the exotic matter, we'd need to arrange it in very specific geometric configurations and control it with incredible precision. The warp bubble has to maintain its shape, move in the direction you want, and remain stable. Some research has shown that certain warp configurations might be inherently unstable, prone to collapse or fluctuation. Imagine trying to surf on a wave made of space-time itself, a wave you also have to generate and control. The engineering challenges are staggering. Third, there are questions about what happens at the boundary of the warp bubble. Some calculations suggest that the edge of the bubble, where normal space-time transitions to warped space-time, could accumulate dangerous amounts of energy or radiation. If you're traveling at effective faster-than-light speeds and then stop, releasing the warp bubble, does all that accumulated energy blast forward like a cosmic deep ray? Could a warp drive accidentally become a weapon of unimaginable power? These are serious questions that researchers are actively exploring. There's also a more fundamental critique emerging from recent research. In February 2026, physicists Hamid Barzagar, Thomas Buchert, and Quentin Vigneron published a comprehensive review of warp drive spacetimes. They systematically examined the various proposals and highlighted what they call misconceptions, misunderstandings, and errors in some of the literature. Their analysis shows that when you apply the principles of general relativity carefully and correctly, many claims about the feasibility of physical warp drives need to be reassessed. They proved several new no-go theorems, mathematical results that place limits on what warp drives can do. Their conclusion is cautious. They argue it's highly challenging to justify the viability of these models, not just because of energy conditions, but because of deeper issues with how these spacetimes behave. This is science working as it should. Bold ideas get proposed, examined, tested, and critiqued. Not every claim survives scrutiny, and that's a good thing. It helps us distinguish between what might actually be possible and what's wishful thinking dressed up in equations. At the same time, other researchers are finding new ways forward. Some are exploring connections between warp drive physics and cosmology, the study of the universe as a whole. During the Big Bang, space itself expanded faster than light. That's not controversial. It's a well-established part of modern cosmology. If space can expand that way naturally, perhaps understanding cosmic expansion could teach us how to create localized regions of space-time expansion and contraction, the exact ingredients needed for a warp drive. Others are looking at numerical simulations rather than purely analytical solutions. In 2025, a team led by Fuchs, Helmerich and Bobrick created what they claim is the first subluminal, energy condition satisfying numerical warp drive solution. It travels slower than light and doesn't violate the known energy conditions that exotic Alcubierre-style drives break. It's not faster than light travel, but it demonstrates that you can create warp-like space-time geometries without requiring impossible physics. It's a proof of principle that could lead to more ambitious designs. There's even research into wormholes, those hypothetical tunnels through space-time that connect distant regions. A March 2026 paper explored traversable wormholes supported by a mechanism called gravitational particle creation. Instead of requiring huge amounts of exotic matter, these wormholes might sustain themselves through quantum processes that create particles from the energy of space-time itself. While wormholes are different from warp drives, they share similar challenges and solutions, and breakthroughs in one area often illuminate the other. So where does all this leave us? We're standing at a genuinely fascinating moment in the history of physics. For the first time, warp drive has moved from pure speculation into serious scientific investigation. We have mathematical models that work within general relativity. We have designs that dramatically reduce the exotic energy requirements. We have computational tools to test and refine these ideas. And we have a growing community of physicists willing to tackle the problem seriously, publishing in peer-reviewed journals and subjecting their work to rigorous critique. At the same time, we remain very far from anything practical. The gap between a promising equation and a working prototype is vast, perhaps unbridgeable with current technology. We might need breakthroughs in quantum field theory, materials science, energy generation, and gravitational control that are decades or even centuries away. Or we might discover tomorrow that some fundamental aspect of physics makes warp drives completely impossible after all. But here's what I find most beautiful about this entire endeavor. The very act of seriously investigating faster-than-light travel pushes us to understand the universe more deeply. Every paper published on warp drive geometry teaches us something new about how space-time works, how energy and matter interact, and what the rules of reality truly allow. Even if we never build a warp drive, the journey toward understanding whether we could is expanding human knowledge. Before we continue, I want to take you back in time to appreciate just how far we've come, because understanding the history of faster-than-light concepts helps us grasp why the current moment is so significant. The dream of traveling to the stars is ancient. For most of human history, we didn't even know what stars were. Ancient civilizations saw them as gods, as tiny holes in the celestial sphere. as distant campfires. It wasn't until the 19th century that astronomers began measuring the true distances to stars and realized the horrifying scale of the cosmos. When Friedrich Bessel made the first successful parallax measurement of a star in 1838, determining that 61 Cygni was about 11 light-years away, the implications were staggering. Light itself, the fastest thing anyone knew, would take 11 years to cover that distance. As physics advanced through the 19th century, scientists came to understand light as an electromagnetic wave. The Scottish physicist James Clerk Maxwell unified electricity and magnetism in his famous equations published in 1865, and those equations predicted that electromagnetic waves should travel at a specific speed, approximately 300,000 kilometers per second. Experiments confirmed this was indeed the speed of light, but a puzzle emerged. According to Newtonian physics, speed should be relative. If you're on a train moving 30 kilometers per hour and you walk forward at 5 kilometers per hour, someone standing still sees you moving at 35 kilometers per hour. So if light travels at 300,000 kilometers per second, shouldn't its speed change depending on whether you're moving toward the light source or away from it? In 1887, two American physicists, Albert Michelson and Edward Morley, conducted an elegant experiment to detect Earth's motion through what was then called the luminiferous ether, the hypothetical medium through which light waves supposedly traveled. They expected to measure differences in the speed of light depending on Earth's direction of motion. The results shocked the scientific world. They measured no difference at all. Light traveled at exactly the same speed in every direction, regardless of Earth's motion. This impossible result lingered like a ghost haunting physics until 1905, when a 26-year-old patent clerk in Bern, Switzerland, published a paper that changed everything. Albert Einstein's special theory of relativity abolished the ether entirely and proposed something radical. The speed of light in vacuum is the same for all observers, regardless of their motion. This wasn't just an interesting fact. It was a fundamental law of nature built into the structure of space and time themselves. The consequences were profound and bizarre. If the speed of light is constant for everyone, then space and time must be flexible, adjustable, relative. Moving clocks tick slower, moving objects contract in length. Events that appear simultaneous to one observer happen at different times for another. And perhaps most relevant to our discussion, nothing with mass can accelerate to light speed. As you approach that ultimate velocity, your mass effectively increases, requiring ever more energy to accelerate further. At exactly light speed, the energy requirement becomes infinite. The universe itself forbids it. This seemed to slam the door on interstellar travel. Even if we could build a spacecraft that traveled at 99% of light speed, the journey to most interesting destinations would still take years, decades, or millennia. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. Even at light speed, the trip would take 2.5 million years, but Einstein wasn't done. In 1915, he published his general theory of relativity, which reframed gravity not as a force, but as the curvature of space-time. Imagine space-time as a flexible fabric. Massive objects create dips and curves in this fabric, and other objects moving through space-time follow the curves. A planet orbiting a star isn't being pulled by a force. It's following the curved path through space-time created by the star's mass. General relativity revealed that space-time is dynamic, flexible, and rich with possibilities. Solutions to Einstein's equations described black holes, regions where space-time curves so severely that nothing, not even light, can escape. They described expanding universes. They even hinted at exotic structures like wormholes, tunnels connecting distant regions of space and time. And here's the crucial insight that reopened the door to faster-than-light dreams. While special relativity forbids objects from moving through space faster than light, general relativity places no such restriction on space itself. Space can expand, contract, and move in ways that seem to violate the cosmic speed limit, because the speed limit only applies to objects moving through space, not to the motion of space itself. This is exactly what happens in cosmic inflation, a theory describing the earliest moments of the Big Bang. According to our best cosmological models, in the first tiny fraction of a second after the universe began, space itself expanded exponentially fast, far faster than light. Regions that were once close together were driven apart so rapidly that light from one could never reach the other. This isn't speculation. We see the consequences in the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. The patterns in that radiation match exactly what inflation theory predicts. If space expanded faster than light in the early universe, could we somehow harness that same mechanism on a smaller scale? Could we create a localized region of rapidly expanding space behind a spacecraft and contracting space in front of it? This is exactly what Miguel Alcubierre wondered when he was a graduate student in the early 1990s. He knew that Einstein's field equations, the mathematical heart of general relativity, allow for many different solutions, each describing a different possible configuration of space-time. Most solutions describe things we observe: stars, planets, black holes, the expanding universe. But the equations are flexible enough to describe exotic possibilities too, as long as they don't violate the mathematical rules. Alcubierre constructed what's called a metric, a mathematical description of the geometry of space-time. His metric described a bubble of flat space-time moving through the surrounding space. Inside the bubble, everything is normal. But at the edges of the bubble, space-time does something remarkable. In front, it contracts, reducing the distance to your destination. Behind, it expands, increasing the distance from your starting point. The bubble itself moves, carrying its contents along. When Alcubierre published his solution in 1994, it proved something important. Faster than light travel doesn't necessarily violate Einstein's general relativity. You're not moving through space faster than light. You're sitting still in your little bubble while space moves around you. It's like standing on a cosmic conveyor belt. The Alcubierre metric sparked immense interest, but also immediate skepticism. The problem was energy. When physicists calculated what kind of matter and energy distribution you'd need to create this warped space-time geometry, they found something deeply troubling. You'd need matter with negative mass or negative energy density. What does that mean? In normal physics, all matter has positive mass and positive energy. It attracts other matter gravitationally. It has inertia. You have to push it to make it move. Negative mass would do the opposite. It would gravitationally repel normal matter. If you pushed it, it would accelerate toward you rather than away from you. It's utterly alien to our everyday experience, and we've never detected anything like it in nature. The amount of negative energy required made the problem even worse. Lawrence Ford and Thomas Roman, physicists who studied the Alcubierre drive carefully, calculated that you'd need negative energy equivalent to the total mass energy of multiple Jupiters. Jupiter has a mass of about 1.9 times 10 to the power of 27 kilograms. We're talking about negative energy equivalent to gas giants or even stars, all arranged in a precise geometric configuration around your spacecraft. Where would you get this energy? How would you contain it? How would you shape it? The engineering challenges were beyond anything humanity had ever contemplated. Most physicists concluded that while the Alcubierre drive was a beautiful mathematical exercise, It had nothing to do with physical reality, but science is full of surprises, and one of them involves something called the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that if you place two uncharged parallel metal plates very close together in a vacuum, they should experience an attractive force. This seems impossible at first. There's nothing between the plates, just empty vacuum, so what could push them together? The answer lies in quantum mechanics. Quantum field theory tells us that what we call empty vacuum isn't actually empty. It's seething with quantum fluctuations, virtual particles popping in and out of existence for incredibly brief moments. These fluctuations create a background energy even in supposedly empty space, sometimes called vacuum energy or zero-point energy. When you place two plates close together, you restrict which quantum fluctuations can exist between them. Only certain wavelengths fit in the narrow gap. Outside the plates, all wavelengths are allowed. This creates an imbalance. There's slightly more quantum vacuum energy outside the plates than between them, and this imbalance creates a tiny attractive force pushing the plates together. In 1997, physicist Steve Lamoureux measured the Casimir effect with extraordinary precision, confirming that it's real. And here's what's crucial. The region between the Casimir plates has less energy than the surrounding vacuum. In a sense, it's a region of negative energy relative to the baseline vacuum energy. This discovery electrified warp drive enthusiasts. Here was actual, measurable, experimentally verified negative energy. Maybe exotic matter wasn't impossible after all. Maybe we just needed to figure out how to amplify and control the Casimir effect. But reality quickly dampened that enthusiasm. The Casimir force is incredibly weak. To measure it, you need plates polished to near perfection, placed a fraction of a micrometer apart in a carefully controlled environment. The energy involved is minuscule. Scaling this up to create the enormous negative energies required for a warp drive would be like trying to power a city with the static electricity from rubbing a balloon on your hair. It's not just difficult, it's absurd given our current understanding and technology. Still, the Casimir effect proved something important. Negative energy isn't forbidden by physics. It exists, at least on tiny scales in very specific circumstances. That kept the door open, however narrowly. Through the late 1990s and early 2000s, a small community of physicists continued exploring warp drive concepts. They refined the mathematics, looked for ways to reduce the energy requirements, and investigated related phenomena. Some focused on wormholes, others on different exotic spacetime geometries. One important development came from a Brazilian physicist named José Natário, who in 2002 proposed an alternative to the Alcubierre drive. The Natário drive used a different mathematical approach but achieved similar results. A bubble of space-time that could carry a spacecraft at faster-than-light effective speeds. Some calculations suggested the Natário approach might require less exotic matter than Alcubierre's design, though it still required enormous amounts. Another researcher, Chris van den Broek, proposed a modified geometry in 1999 that dramatically reduced the total energy requirement. His design involved creating a warp bubble with a very small interior volume but a much larger internal space, kind of like a TARDIS from Doctor Who, bigger on the inside. This reduced the amount of exotic matter needed by many orders of magnitude, though the amounts were still enormous by any practical standard, and the design introduced new complications. Harold White, then at NASA's Johnson Space Center, made headlines in 2012 when he announced that his team was investigating warp drive physics and had calculated that a modification to the Alcubierre metric might reduce the energy requirement to something closer to the mass of the Voyager 1 spacecraft, roughly 722 kilograms. This was still an enormous amount of exotic negative energy, far beyond anything we could produce, but it was a far cry from needing Jupiter-scale masses. White's work was intriguing but controversial. Some physicists questioned whether his modifications truly reduced the energy requirements, or whether they just redistributed them in ways that were harder to measure. Others pointed out that even if the total energy was reduced, you still face the impossible task of creating and manipulating exotic matter with negative mass. Throughout the 2010s, warp drive research remained a fringe topic, pursued by a handful of dedicated physicists, but largely dismissed by the mainstream scientific community. The consensus was clear: interesting mathematics, but not physically realizable. The exotic matter problem seemed insurmountable, and even if you could somehow obtain negative energy, the quantities required were so vast that practical implementation was utterly beyond reach. Then came the paper that changed the conversation. In March of 2021, Alexei Bobrik, an astrophysicist, and Gianni Martire, a physicist and engineer, published a paper titled Introducing Physical Warp Drives. Their work didn't claim to have solved the warp drive problem, but it did something perhaps more important. It reframed the entire question. Bobrik and Martire argued that previous research had focused too narrowly on superluminal warp drives, those traveling faster than light. They proposed a broader classification system that included subluminal warp drives, ones that travel slower than light but still use the same basic principle of warping spacetime to move. And here's their key insight: for certain subluminal configurations, you might not need exotic negative energy at all. You could potentially create a warp bubble using only positive energy, the kind of energy that actually exists and that we know how to manipulate. Think about what this means. The original Alcubierre drive required you to solve two impossible problems simultaneously: figure out how to create exotic negative energy and figure out how to generate it in planet-scale quantities. Bobrik and Martire's work suggested that maybe you only need to solve one problem: generating enough regular positive energy and arranging it in the right geometric configuration. That's still incredibly difficult, requiring energy levels far beyond our current capabilities, but it's not impossible in principle. It doesn't require discovering new physics or new types of matter. Their paper was careful and rigorous. They didn't oversell their results or claim that warp drives were just around the corner. Instead, they provided a mathematical framework for understanding the full spectrum of possible warp drive geometries and showed that some regions of that spectrum might be physically accessible. The scientific community's response was mixed. Some physicists welcomed the fresh perspective and appreciated the careful mathematical treatment. Others remained skeptical, arguing that even subluminal warp drives faced severe practical challenges and that the positive energy solutions came with their own set of problems, including potential instabilities and the difficulty of initiating and controlling the warp field. But the paper accomplished something crucial. It made warp drive research respectable again. Major scientific journals began publishing warp drive papers more regularly. Conferences included sessions on advanced propulsion concepts. Young physicists could work on warp drive theory without jeopardizing their careers. The field was no longer purely speculative. It had become a legitimate area of theoretical investigation. This brings us to the recent breakthroughs, the developments that have emerged just in the past year, and that represent the most significant progress yet. In December of 2025, a researcher named Rodal published a remarkable paper in the journal General Relativity and Gravitation. The title was technical: a warp drive with predominantly positive invariant energy density and global Hawking-Ellis Type 1, but the implications were profound. Rodal had constructed something that had eluded researchers for 3 decades, a fully explicit, continuous analytically derived warp drive spacetime that is irrotational. Let me break down why each of those characteristics matters. Fully explicit means that every component of the spacetime geometry is written out in complete mathematical detail. You're not making approximations or leaving parts undefined. You have the exact solution. Continuous means the geometry is smooth, without jumps or discontinuities that could cause problems or signal unphysical behavior. Analytically derived means it's expressed in terms of standard mathematical functions, not just numerical approximations. This makes it much easier to analyze, understand, and modify, and irrotational is the key feature that sets Rodal's solution apart from almost everything that came before. To understand why irrotationality matters, we need to talk about vorticity. In fluid dynamics, vorticity describes the local rotation or spinning motion within a flow. Water going down a drain has vorticity. It's swirling. Water flowing smoothly through a straight pipe without spinning has zero vorticity. It's irrotational. In the context of warp drives, vorticity describes a kind of twisting or spinning character in how the spacetime distortion moves. The original Alcubierre drive and most subsequent designs had vorticity. The warp field wasn't just moving forward, it had a kind of internal rotation or circulation to it. Why does this matter? Because vorticity dramatically increases the stress and strain on space-time. It creates instabilities, makes the geometry harder to maintain, and most importantly, it massively increases the amount of exotic negative energy you need. The spinning, turbulent character of a vortical warp field fights against itself, requiring enormous energy input to sustain. Rodal's irrotational design eliminates this problem. The warp field flows smoothly, without internal rotation, and the results are spectacular. When Rodal and colleagues calculated the energy requirements for this new geometry and compared them to previous designs using identical parameters, the same bubble size, the same wall thickness, the same velocity, they found that the peak negative energy density was reduced by a factor of approximately 38 compared to the original Alcubierre drive. 38 times less exotic matter needed for the same performance, compared to the Nacelle drive, which many researchers had considered promising. The reduction was even more dramatic. Approximately 2,600 times less negative energy required. But it gets better. When they looked at violations of the null energy condition, one of the fundamental energy conditions in general relativity, Rodal's design showed violations more than 60 times smaller than the Nacelle drive. And here's perhaps the most astonishing result. When they calculated the total proper energy density across the entire warp bubble, integrating over the whole structure, they found that the positive energy and negative energy components balanced out to essentially zero. Not exactly zero, physics doesn't usually give you perfect cancellations, but 0 to 4 decimal places. The net exotic energy requirement might be vanishingly small. Let me emphasize what this doesn't mean. It doesn't mean the warp drive is free. You still need energy to create the specific geometric configuration, to initiate the warp field, and to maintain it. Think of it like this. Balancing a pencil on its tip requires very little force once it's balanced, but getting it into that balanced state and keeping it there requires constant tiny adjustments. Similarly, Rodal's warp drive might have a net energy close to zero, but creating and stabilizing that configuration still demands significant power. Nevertheless, this is a breakthrough. It shows that with the right geometry, with careful attention to the mathematical structure of the space-time, you can create warp drive solutions that are far, far less exotic than anyone previously thought possible. Rodal's work demonstrated something else important. The reduction in exotic energy isn't due to some mathematical trick or clever accounting. It's causally linked to the irrotational nature of the field. To prove this, the researchers conducted what they called a vortical ablation study. They took their irrotational design and deliberately added small amounts of vorticity to it, creating a slightly spinning warp field. Then they recalculated the energy requirements. The results were clear. Even modest amounts of vorticity collapsed the careful energy balance. The positive and negative energy components stopped cancelling out. The magnitude of the negative energy requirement shot upward. This proved that the improvement wasn't about the shape of the bubble or some other geometric feature. It was specifically because the flow was irrotational. This has enormous implications for future research. It tells us that if we want to make practical warp drives, we need to focus on designs that minimize or eliminate vorticity. We need smooth laminar flow in our spacetime distortions, not turbulent, spinning geometries. Almost simultaneously, in the same month of December 2025, Harold White and his colleagues published another significant paper in the journal Classical and Quantum Gravity. They presented what they call interior flat cylindrical nacelle warp bubbles. Previous warp drive designs, including Alcubierre's and Rodal's, typically assumed a smooth, continuous distribution of exotic matter around the spacecraft, like a shell or a bubble surrounding you. White's team asked a different question. What if, instead of one continuous bubble, we created multiple discrete channels of warped space-time arranged around the vessel? Imagine a spacecraft with several cylindrical nacelles. Think of the warp nacelles on the Starship Enterprise if you're a Star Trek fan, positioned symmetrically around the hull. Each nacelle generates a localized region of exotic space-time curvature. Together, these cylindrical regions combine to create the overall warp effect, propelling the ship forward. This design has several advantages. First, it localizes the exotic matter into specific, confined regions rather than spreading it throughout a continuous shell. This might make it easier to generate, contain, and control. Think of it like the difference between trying to create a uniform glow across an entire ceiling versus installing several discrete light fixtures. The latter is usually much easier to engineer. Second, White's design ensures that the interior region, where the passengers and cargo sit, remains flat. In general relativity, flat spacetime is special. It's the baseline, the geometry of empty space far from any mass or energy. When spacetime is flat, clocks tick at their normal rate, straight lines are straight, and physics behaves in the familiar ways we're used to. This matters because some warp drive geometries create curved spacetime inside the bubble. This could lead to tidal forces stretching and compressing objects, or it could cause time dilation, where time passes at a different rate inside the bubble than outside. White's interior flat design avoids these problems. You could sit comfortably inside your warp bubble, experiencing normal gravity, normal time flow, and no exotic tidal effects. While the universe rearranges itself around you, the team used sophisticated numerical methods and visualization tools to map out the energy density, the curvature, and the boost magnitude throughout their warp bubble geometry. They created three-dimensional isosurfaces, mathematical surfaces showing where the energy density or curvature reaches specific values, and these visualizations revealed the complex structure of the warp field in stunning detail. Their calculations showed that by segmenting the exotic energy into cylindrical nacelles, you could achieve warp drive performance comparable to continuous shell designs while potentially making the engineering more manageable. You're not reducing the total exotic energy required. That still depends on the size of the bubble and the velocity you want, but you're changing how that energy is distributed. And distribution matters enormously for practical implementation. Another crucial development came in February of 2026 with the development of a computational tool called Warpax. Created by researcher Antile, Warpax is a software package built on JAX, a high-performance numerical computing framework specifically designed to analyze the energy conditions of warp drive spacetimes. Here's why this matters. When you propose a new warp drive geometry, you need to check whether it violates energy conditions, and if so, how severely. Energy conditions are statements about what kinds of energy distributions are physically reasonable. The weak energy condition says that energy density should never be negative in any reference frame. The null energy condition says that energy flow along light rays should never be negative. Various other conditions impose similar constraints. Exotic warp drives violate these conditions. That's what makes them exotic. But you want to know precisely where the violations occur, how severe they are, and whether they're the same for all observers or change depending on your reference frame. Previous methods for checking energy conditions often relied on choosing a specific reference frame, usually the natural frame of the spacetime itself. But here's a problem. Energy conditions can look different depending on who's observing. A configuration that barely violates the weak energy condition in one frame might grossly violate it in another frame. If you only check one frame, you might miss the full picture. Warpax solves this by using frame-independent methods based on the eigenvalues of the stress-energy tensor, a mathematical object that encodes how energy and momentum are distributed throughout space-time. Eigenvalues are boost invariants, meaning they're the same regardless of your reference frame. By analyzing these eigenvalues, Warpax can definitively classify each point in the spacetime as either Hawking-Ellis type 1, which has a well-defined rest frame and might satisfy energy conditions, or type 4, which has no rest frame and violates all energy conditions unconditionally. When they applied Warpax to various warp drive geometries, the results were revealing. The tool showed a clean dichotomy, a fundamental split in the family of warp drives. Rodal's irrotational geometry remained type 1 everywhere at all speeds. The Alcubierre, Natario, and Van den Broek designs, all of which have vorticity, showed regions dominated by type 4 violations, especially in the bubble wall. The analysis made it quantitative. Warpax calculated that the irrotational Rodal drive ranked 45 to 70 times lower in what they called an exoticity metric, a measure of how severely a geometry violates normal physics, compared to the vortical bubble wall drives. This confirmed Rodal's earlier findings using a completely different mathematical approach. Even more interesting, Warpax revealed patterns that single-frame analyses missed. For the Rodal drive, if you only analyze the energy conditions in the Eulerian frame, the natural resting frame of the spacetime, you'd miss about 72% of the weak energy violations that boosted observers, people moving relative to the warp bubble, would actually see. This shows how crucial it is to use frame-independent methods. What looks acceptable in one perspective might be highly problematic in another. These computational tools are transforming warp drive research from purely theoretical speculation into something more like aerospace engineering. You can now test designs, optimize parameters, compare alternatives, and identify problems before you ever try to build anything. It's the same progression that happened in aircraft design, when wind tunnels and computer simulations allowed engineers to test thousands of configurations cheaply and quickly before committing to expensive prototypes. But perhaps the most important recent development isn't a single paper or breakthrough. It's the growing recognition within the physics community that warp drive research is asking the right questions. Even if we don't yet have the right answers, throughout the 2010s, warp drive research remained a fringe topic, pursued by a handful of dedicated physicists, but largely dismissed by the mainstream scientific community. The consensus was clear. Interesting mathematics, but not physically realizable. The exotic matter problem seemed insurmountable, and even if you could somehow obtain negative energy, the quantities required were so vast that practical implementation was utterly beyond reach. Then came the paper that changed the conversation. In March of 2021, Alexei Bobrik, an astrophysicist, and Gianni Martire, a physicist and engineer, published a paper titled Introducing Physical Warp Drives. Their work didn't claim to have solved the warp drive problem, but it did something perhaps more important. It reframed the entire question. Bobrik and Martire argued that previous research had focused too narrowly on superluminal warp drives, those traveling faster than light. They proposed a broader classification system that included subluminal warp drives, ones that travel slower than light but still use the same basic principle of warping spacetime to move. And here's their key insight. For certain subluminal configurations, you might not need exotic negative energy at all. You could potentially create a warp bubble using only positive energy, the kind of energy that actually exists and that we know how to manipulate. Think about what this means. The original Alcubierre drive required you to solve two impossible problems simultaneously. Figure out how to create exotic negative energy and figure out how to generate it in planet-scale quantities. Bobrik and Martire's work suggested that maybe you only need to solve one problem, generating enough regular positive energy and arranging it in the right geometric configuration. That's still incredibly difficult, requiring energy levels far beyond our current capabilities, but it's not impossible in principle. It doesn't require discovering new physics or new types of matter. Their paper was careful and rigorous. They didn't oversell their results or claim that warp drives were just around the corner. Instead, they provided a mathematical framework for understanding the full spectrum of possible warp drive geometries and showed that some regions of that spectrum might be physically accessible. The scientific community's response was mixed. Some physicists welcomed the fresh perspective and appreciated the careful mathematical treatment. Others remained skeptical, arguing that even subluminal warp drives faced severe practical challenges and that the positive energy solutions came with their own set of problems, including potential instabilities and the difficulty of initiating and controlling the warp field. But the paper accomplished something crucial. It made warp drive research respectable again. Major scientific journals began publishing warp drive papers more regularly. Conferences included sessions on advanced propulsion concepts. Young physicists could work on warp drive theory without jeopardizing their careers. The field was no longer purely speculative. It had become a legitimate area of theoretical investigation. This brings us to the recent breakthroughs, the developments that have emerged just in the past year, and that represent the most significant progress yet. In December of 2025, a researcher named Rodal published a remarkable paper in the journal General Relativity and Gravitation. The title was Technical, a warp drive with predominantly positive invariant energy density and global Hawking-Ellis Type 1, but the implications were profound. Rodal had constructed something that had eluded researchers for 3 decades, a fully explicit, continuous, analytically derived warp drive spacetime that is irrotational. Let me break down why each of those characteristics matters. Fully explicit means that every component of the spacetime geometry is written out in complete mathematical detail. You're not making approximations or leaving parts undefined. You have the exact solution. Continuous means the geometry is smooth, without jumps or discontinuities that could cause problems or signal unphysical behavior. Analytically derived means it's expressed in terms of standard mathematical functions, not just numerical approximations. This makes it much easier to analyze, understand, and modify, and irrotational is the key feature that sets Rodal's solution apart from almost everything that came before. To understand why irrotationality matters, we need to talk about vorticity. In fluid dynamics, vorticity describes the local rotation or spinning motion within a flow. Water going down a drain has vorticity. It's swirling. Water flowing smoothly through a straight pipe without spinning has zero vorticity. It's irrotational. In the context of warp drives, vorticity describes a kind of twisting or spinning character in how the spacetime distortion moves. The original Alcubierre drive and most subsequent designs had vorticity. The warp field wasn't just moving forward, it had a kind of internal rotation or circulation to it. Why does this matter? Because vorticity dramatically increases the stress and strain on spacetime. It creates instabilities, makes the geometry harder to maintain, and most importantly, it massively increases the amount of exotic negative energy you need. The spinning, turbulent character of a vortical warp field fights against itself, requiring enormous energy input to sustain. Rodal's irrotational design eliminates this problem. The warp field flows smoothly, without internal rotation. And the results are spectacular. When Rodal and colleagues calculated the energy requirements for this new geometry and compared them to previous designs using identical parameters, the same bubble size, the same wall thickness, the same velocity, they found that the peak negative energy density was reduced by a factor of approximately 38 compared to the original Alcubierre drive. 38 times less exotic matter needed for the same performance compared to the Nacelle drive, which many researchers had considered promising. The reduction was even more dramatic. Approximately 2,600 times less negative energy required, but it gets better. When they looked at violations of the null energy condition, one of the fundamental energy conditions in general relativity, Rodal's design showed violations more than 60 times smaller than the Nacelle drive. And here's perhaps the most astonishing result. When they calculated the total proper energy density across the entire warp bubble, integrating over the whole structure, they found that the positive energy and negative energy components balanced out to essentially zero. Not exactly zero, physics doesn't usually give you perfect cancellations, but 0 to 4 decimal places. The net exotic energy requirement might be vanishingly small. Let me emphasize what this doesn't mean. It doesn't mean the warp drive is free. You still need energy to create the specific geometric configuration, to initiate the warp field, and to maintain it. Think of it like this. Balancing a pencil on its tip requires very little force once it's balanced, but getting it into that balanced state and keeping it there requires constant tiny adjustments. Similarly, Rodal's warp drive might have a net energy close to zero, but creating and stabilizing that configuration still demands significant power. Nevertheless, this is a breakthrough. It shows that with the right geometry, with careful attention to the mathematical structure of the space-time, you can create warp drive solutions that are far, far less exotic than anyone previously thought possible. Rodal's work demonstrated something else important. The reduction in exotic energy isn't due to some mathematical trick or clever accounting. It's causally linked to the irrotational nature of the field. To prove this, the researchers conducted what they called a vortical ablation study. They took their irrotational design and deliberately added small amounts of vorticity to it, creating a slightly spinning warp field. Then they recalculated the energy requirements. The results were clear. Even modest amounts of vorticity collapsed the careful energy balance. The positive and negative energy components stopped cancelling out. The magnitude of the negative energy requirement shot upward. This proved that the improvement wasn't about the shape of the bubble or some other geometric feature. It was specifically because the flow was irrotational. This has enormous implications for future research. It tells us that if we want to make practical warp drives, we need to focus on designs that minimize or eliminate vorticity. We need smooth laminar flow in our spacetime distortions, not turbulent, spinning geometries almost simultaneously. In the same month of December 2025, Harold White and his colleagues published another significant paper in the journal Classical and Quantum Gravity. They presented what they call interior flat cylindrical nacelle warp bubbles. Previous warp drive designs, including Alcubierre's and Rodal's, typically assumed a smooth, continuous distribution of exotic matter around the spacecraft, like a shell or a bubble surrounding you. White's team asked a different question. What if instead of one continuous bubble, we created multiple discrete channels of warped space-time arranged around the vessel? Imagine a spacecraft with several cylindrical nacelles. Think of the warp nacelles on the Starship Enterprise if you're a Star Trek fan, positioned symmetrically around the hull. Each nacelle generates a localized region of exotic spacetime curvature. Together, these cylindrical regions combine to create the overall warp effect, propelling the ship forward. This design has several advantages. First, it localizes the exotic matter into specific, confined regions rather than spreading it throughout a continuous shell. This might make it easier to generate, contain, and control. Think of it like the difference between trying to create a uniform glow across an entire ceiling versus installing several discrete light fixtures. The latter is usually much easier to engineer. Second, White's design ensures that the interior region, where the passengers and cargo sit, remains flat. In general relativity, flat spacetime is special. It's the baseline, the geometry of empty space far from any mass or energy. When spacetime is flat, clocks tick at their normal rate, straight lines are straight, and physics behaves in the familiar ways we're used to. This matters because some warp drive geometries create curved spacetime inside the bubble. This could lead to tidal forces stretching and compressing objects, or it could cause time dilation, where time passes at a different rate inside the bubble than outside. White's interior flat design avoids these problems. You could sit comfortably inside your warp bubble, experiencing normal gravity, normal time flow, and no exotic tidal effects. While the universe rearranges itself around you, the team used sophisticated numerical methods and visualization tools to map out the energy density, the curvature, and the boost magnitude throughout their warp bubble geometry. They created three-dimensional isosurfaces, mathematical surfaces showing where the energy density or curvature reaches specific values, and these visualizations revealed the complex structure of the warp field in stunning detail. Their calculations showed that by segmenting the exotic energy into cylindrical nacelles, you could achieve warp drive performance comparable to continuous shell designs, while potentially making the engineering more manageable. You're not reducing the total exotic energy required. That still depends on the size of the bubble and the velocity you want, but you're changing how that energy is distributed, and distribution matters enormously for practical implementation. Another crucial development came in February of 2026 with the development of a computational tool called Warpax. Created by researcher Antile, Warpax is a software package built on JAX, a high-performance numerical computing framework specifically designed to analyze the energy conditions of warp drive spacetimes. Here's why this matters. When you propose a new warp drive geometry, you need to check whether it violates energy conditions, and if so, how severely. Energy conditions are statements about what kinds of energy distributions are physically reasonable. The weak energy condition says that energy density should never be negative in any reference frame. The null energy condition says that energy flow along light rays should never be negative. Various other conditions impose similar constraints, Exotic warp drives violate these conditions. That's what makes them exotic. But you want to know precisely where the violations occur, how severe they are, and whether they're the same for all observers or change depending on your reference frame. Previous methods for checking energy conditions often relied on choosing a specific reference frame, usually the natural frame of the spacetime itself. But here's a problem. Energy conditions can look different depending on who's observing. A configuration that barely violates the weak energy condition in one frame might grossly violate it in another frame. If you only check one frame, you might miss the full picture. Warpax solves this by using frame-independent methods based on the eigenvalues of the stress-energy tensor, a mathematical object that encodes how energy and momentum are distributed throughout space-time. Eigenvalues are boost invariants, meaning they're the same regardless of your reference frame. By analyzing these eigenvalues, Warpax can definitively classify each point in the spacetime as either Hawking-Ellis type 1, which has a well-defined rest frame and might satisfy energy conditions, or type 4, which has no rest frame and violates all energy conditions unconditionally. When they applied Warpax to various warp drive geometries, the results were revealing. The tool showed a clean dichotomy, a fundamental split in the family of warp drives. Rodal's irrotational geometry remained type 1 everywhere, at all speeds. The Alcubierre, Notario and Van den Broek designs, all of which have vorticity, showed regions dominated by type 4 violations, especially in the bubble wall. The analysis made it quantitative. Warpax calculated that the irrotational Rodal drive ranked 45 to 70 times lower in what are called an exoticity metric, a measure of how severely a geometry violates normal physics, compared to the vortical bubble wall drives. This confirmed Rodal's earlier findings using a completely different mathematical approach. Even more interesting, Warpax revealed patterns that single-frame analyses missed. For the Rodal drive, if you only analyze the energy conditions in the Eulerian frame, the natural resting frame of the spacetime, you'd miss about 72% of the weak energy violations that boosted observers, people moving relative to the warp bubble, would actually see. This shows how crucial it is to use frame-independent methods. What looks acceptable in one perspective might be highly problematic in another. These computational tools are transforming warp drive research from purely theoretical speculation into something more like aerospace engineering. You can now test designs, optimize parameters, compare alternatives, and identify problems before you ever try to build anything. It's the same progression that happened in aircraft design when wind tunnels and computer simulations allowed engineers to test thousands of configurations cheaply and quickly before committing to expensive prototypes. But perhaps the most important recent development isn't a single paper or breakthrough. It's the growing recognition within the physics community that warp drive research is asking the right questions, even if we don't yet have the right answers. In April of 2026, physicists Thomas Buchert and his colleagues published a comprehensive paper titled Novel Realizations of Warp Drive Spacetimes as Solutions of General Relativity. This wasn't just another proposal for a new warp drive design. It was a systematic framework for understanding how warp fields might actually work within the broader context of Einstein's theory. Buchert's team did something fascinating. They connected warp drive physics to cosmology, the study of the universe as a whole. At first, this might seem like an odd connection. What does a tiny bubble carrying a spacecraft have to do with the evolution of the entire cosmos? But the link is profound. In cosmology, we describe the universe using what's called the Friedmann-Lemaitre-Robertson-Walker metric, a solution to Einstein's equations that describes an expanding, homogeneous universe. This metric tells us that space itself is expanding, carrying galaxies apart. Crucially, This expansion can occur at any speed. During cosmic inflation in the first fraction of a second after the Big Bang, space expanded far faster than light. This doesn't violate relativity because space itself is expanding, not objects moving through space. Buchert realized that warp drives are essentially localized, controlled versions of cosmic expansion and contraction. Instead of the entire universe expanding uniformly, you create a small region where space contracts in front and expands behind. The mathematics that describes cosmic expansion should, with appropriate modifications, also describe warp bubbles. This connection opens up powerful new tools. Cosmologists have developed sophisticated mathematical techniques over decades to handle expanding spacetimes, to understand their stability, to track how matter and energy evolve within them. Many of these techniques can be adapted to study warp drives. Buchert's team used what's called a relativistic Lagrangian perturbation approach, a method originally developed to study how galaxies and cosmic structures form in an expanding universe. They applied this framework to warp fields and discovered something important. There's a direct correspondence between certain solutions of Newtonian gravity and solutions of general relativity that describe warp-like geometries. This is huge because Newtonian gravity, despite being superseded by general relativity, is much simpler mathematically. If you can solve a problem in Newtonian gravity and then translate that solution into general relativity, you've found a shortcut. It's like having a map of a complicated city where some streets correspond to simple grid patterns. Navigate the grid, then translate your position back to the real streets. The paper also addressed a critical issue that had been largely ignored in earlier work: the dynamics of warp fields. Most warp drive research treats the warp bubble as static or assumes it's already formed and moving. But how do you create a warp bubble in the first place? How do you accelerate it, turn it, or bring it to a stop? What happens during these transitions? Buchert's framework allows for the description of warp field dynamics, treating the bubble not as a fixed structure, but as an evolving system. Their analysis revealed that certain warp configurations might be inherently unstable. Imagine trying to balance a marble on top of an upside-down bowl. In principle, if you could place it exactly at the peak and release it with zero velocity, it would stay there, but in practice, the tiniest perturbation sends it rolling off. Some warp geometries are like that marble, theoretically possible but practically unstable. The instability arises from what the researchers call coordinate vorticity and coordinate acceleration. These are mathematical properties describing how the space-time coordinates themselves, twist and accelerate within the warp field. When these properties exceed certain thresholds, the warp field becomes dynamically unstable. It wants to collapse, deform, or evolve into a different configuration. This finding has practical implications. If we ever hope to build a real warp drive, we need to understand not just what stable configurations look like, but how to reach those configurations and maintain them against perturbations. It's the difference between knowing the design for a bridge and knowing how to actually construct it so it doesn't collapse during or after construction. Buchert's team concluded by discussing possible future paths toward physical warp drives within what they call tilted fluid flows. This is a technical concept from cosmology describing situations where matter doesn't just sit still in an expanding universe but flows, creating currents and structure. The suggestion is that understanding these tilted flows might provide clues about how to generate and control warp fields using realistic matter distributions rather than purely exotic negative energy. While this research was unfolding, another group was tackling the problem from a completely different angle. In February 2026, Hamed Barzigar, Thomas Buchert, and Quentin Vigneron published a critical analysis titled general formalism, classification, and demystification of the current warp drive spacetimes. This paper was the cold shower the field needed. The authors systematically examined all the major warp drive proposals and classifications, applying rigorous mathematical scrutiny to each claim. They identified what they called misconceptions, misunderstandings, and outright errors in some of the published literature. Their analysis wasn't trying to kill the field or claim warp drives are impossible. Rather, it was doing what science is supposed to do, separating wishful thinking from solid reasoning, distinguishing between what the mathematics actually proves and what people hope it proves. Barzagar and colleagues proved several new no-go theorems. These are mathematical statements that place fundamental limits on what's possible. For example, they showed that certain claimed advantages of modified warp drive geometries disappear when you apply Einstein's equations correctly. Some proposed designs that supposedly reduced energy requirements only appeared to do so because of calculation errors or incomplete analysis. The paper emphasized that when you apply the principles of general relativity carefully, consistently, and completely, most claims about the physicality and feasibility of warp drives must be reassessed. The challenges aren't just about energy conditions or exotic matter. There are deeper issues with causality, with the global structure of the space-time, and with the physical interpretation of the mathematical solutions. One crucial point they raised involves something called the shift vector, a mathematical object that describes how space is being dragged or moved in the warp drive geometry. Many warp drive solutions assume you can simply specify the shift vector however you want, choosing it to give you the motion you desire. But the shift vector isn't arbitrary. It's constrained by Einstein's equations. You can't just decree that space will move in a particular way. You have to show that such motion is consistent with the energy and matter distribution, and that such a distribution is physically possible. When Barzagar and colleagues carefully examined this issue, they found that many proposed warp drives had inconsistencies. The shift vector implied an energy distribution that was even more exotic than previously calculated, or it required boundary conditions, specifications of what happens at the edges of the space-time that couldn't be physically realized. This critical analysis might sound discouraging, and indeed it showed that some of the more optimistic claims about warp drives were overblown. But it also performed an essential service. It clarified what we actually know versus what we merely hope. It identified which lines of research are most promising and which are dead ends. And it set higher standards for future work, ensuring that new proposals would be more rigorous and reliable. Science advances through this dialectic between bold speculation and rigorous critique. You need visionaries willing to explore radical ideas, and you need skeptics willing to tear those ideas apart and see what survives. Both Rodal's groundbreaking irrotational warp drive and Barzagar's critical analysis are essential parts of the same process. Meanwhile, other researchers were exploring the observational signatures of warp drives and related exotic objects. If warp bubbles or similar spacetime distortions exist anywhere in the universe, how would we detect them? What would they look like? In March 2026, a team published research on traversable wormholes, which share many mathematical properties with warp drives. They investigated what's called the shadow structure, the apparent shape and darkness you'd see if you looked at a wormhole against a background of stars or light. They also calculated quasi-normal modes, the characteristic frequencies at which the space-time around such an object would vibrate if disturbed. Like ringing a bell, these calculations matter because they're potentially testable. If we ever detected a mysterious compact object in space that cast a shadow with a specific, unusual shape, or if we detected gravitational waves with quasi-normal frequencies that don't match black holes or neutron stars, we might be seeing evidence of exotic space-time structures. The team also investigated gray body factors, which describe how much radiation can escape from near an exotic object versus how much gets trapped or reflected. Every type of compact object, black holes, neutron stars, hypothetical wormholes, or warp bubbles, has its own characteristic gray body spectrum. In principle, precise astronomical observations could distinguish between them. This research is speculative since we've never detected anything like a wormhole or warp bubble in nature, but it prepares us. If exotic space-time structures exist anywhere in the cosmos, either naturally occurring or perhaps created by advanced civilizations, we now have some idea what to look for. There's also been fascinating work on the energy requirements from a different perspective. Some researchers have asked, instead of minimizing the exotic negative energy, could we find ways to generate the enormous positive energies that even the improved designs require? The energy scales involved are staggering, even with Rodal's optimized geometry. Creating a warp bubble large enough to carry a spacecraft would require harnessing energy equivalent to significant fractions of a star's total output. We're talking about power levels measured in the thousands or millions of terawatts, sustained not just for an instant, but for the duration needed to create, accelerate, and maintain the warp field. For perspective, the entire human civilization currently uses about 18 terawatts of power across all energy sources, fossil fuels, nuclear, renewables, everything. A modest warp drive might need 10,000 times that much power. Where would it come from? Some proposals involve antimatter. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation E=mc². This is by far the most efficient energy source allowed by known physics. A single kilogram of antimatter annihilating with a kilogram of matter releases energy equivalent to 43 megatons of TNT, roughly the yield of the largest nuclear weapon ever detonated. If you could somehow produce, store and control antimatter in large quantities, you might generate the power needed for a warp drive. But antimatter production is currently absurdly inefficient. The Large Hadron Collider, the world's most powerful particle accelerator, produces only a few nanograms of antimatter per year. Scaling up to the kilograms or tons you'd need for a warp drive would require technological advances we can barely imagine. Others have suggested harnessing the energy of black holes through the Penrose process or similar mechanisms. Rotating black holes have a region called the ergosphere, where spacetime itself is dragged along with the black hole's rotation. If you could carefully drop matter into the ergosphere and extract it at the right trajectory, you could in theory extract energy from the black hole's rotation, potentially achieving efficiencies of up to 29% mass-to-energy conversion for a maximally rotating black hole. But this requires parking your civilization next to a black hole and developing the technology to manipulate objects in the most extreme gravitational environment in the universe. It's not something humanity will be doing anytime soon. The most speculative proposals involve vacuum energy. Remember the Casimir effect, where quantum fluctuations in empty space create measurable forces. The vacuum of space contains energy, potentially enormous amounts of it. Some quantum field theory calculations suggest the vacuum energy density should be incredibly high, though observations show it's actually very low, a discrepancy called the cosmological constant problem, one of the deepest unsolved mysteries in physics. If we could somehow tap vacuum energy, extract usable power from the quantum foam of spacetime itself, we'd have an effectively limitless energy source. But we have no idea how to do this. The Casimir effect shows vacuum energy is real, but extracting useful amounts of it is pure speculation at this point. What's becoming clear from all this research is that warp drives, even the optimized versions that minimize exotic matter requirements, demand technologies so advanced that they might belong to civilizations far beyond our current level. We're talking about Type 2 civilizations on the Kardashev scale, societies capable of harnessing the entire energy output of their home star. For context, humanity is currently about a Type 0.7 civilization. We use a fraction of the energy that reaches Earth from the Sun. Reaching Type 1, using all the energy our planet receives, might take a century or two with continued technological progress. Reaching Type 2 could take thousands of years or more. This raises a fascinating question. If warp drives are possible but require Type 2 technology, might they already exist somewhere in the universe? Could advanced alien civilizations be using warp drives right now, traveling between stars while we're still struggling with chemical rockets? This possibility has profound implications for the search for extraterrestrial intelligence, or SETI. Traditional SETI focuses on detecting radio signals or optical flashes that might represent alien communications. But if warp drives are possible, we should also search for their signatures. What would a warp drive look like from a distance? This is where the physics gets particularly interesting. A warp bubble moving through space would create distinctive gravitational effects. As it passes near a star, the warped spacetime would bend light rays in unusual ways, creating distortions and potentially brief brightenings or dimmings of the star, as seen from Earth. The pattern would be different from planets, different from eclipsing binary stars, different from anything natural we know. There's also the question of radiation. Some calculations suggest that the boundary region of a warp bubble, where space-time transitions from the contracted region in front to the expanded region behind, might emit intense radiation, possibly including Hawking radiation, similar to what theoretical black holes produce. A warp bubble moving at high speeds might blaze with high-energy photons visible across interstellar distances. In 2024, a team of researchers led by Jamie Parr published a paper exploring the detectability of warp drives. They calculated that if a warp bubble passed through our solar system, our most sensitive gravitational wave detectors might pick up the signal. The frequency and pattern would be unlike anything from merging black holes or neutron stars the signals LIGO and Virgo have been detecting since 2015. It would be a unique signature, potentially unmistakable. They also noted that the Event Horizon Telescope, the global network of radio telescopes that captured the first image of a black hole in 2019, might be able to detect warp drive signatures, if any existed in nearby galaxies. The same interferometric techniques that resolve the shadow of a black hole millions of light-years away could potentially image the space-time distortions around a warp bubble. So far, we've detected nothing of the sort, but we've only been looking with sufficient sensitivity for a few years, and we've only examined a tiny fraction of the sky in detail. The absence of evidence isn't evidence of absence, especially when the search space is so vast. There's another intriguing angle. Perhaps we've already seen warp drive signatures, but didn't recognize them. Space is full of mysterious phenomena. Fast radio bursts, millisecond duration blasts of radio energy from distant galaxies were only discovered in 2007, and we still don't fully understand what causes them. Most are probably natural, likely involving magnetars or neutron stars, but some show puzzling properties that challenge our explanations. Oumuamua, the first confirmed interstellar object detected passing through our solar system in 2017, exhibited strange acceleration that couldn't be entirely explained by ordinary gravitational forces or outgassing like a comet. Most scientists think it was probably an unusual natural object, perhaps a nitrogen iceberg or a fragment of a disrupted planet, but its properties sparked significant debate. I'm not suggesting Oumuamua was an alien spacecraft with a warp drive. The evidence doesn't support that, and extraordinary claims require extraordinary evidence. But these examples illustrate how much we still don't understand about what's out there. If exotic technologies exist, we need to know what to look for, and that requires theoretical work like the warp drive research we've been discussing. Let me also address the elephant in the room: causality and time travel. One of the deepest concerns about warp drives isn't the energy requirement or exotic matter. It's that they might allow you to travel backward in time, violating causality and creating paradoxes. Here's how the problem arises. In special relativity, simultaneity is relative. Events that appear to happen at the same time for one observer happen at different times for another observer, moving relative to the first. When you combine this with faster-than-light travel, even if it's achieved through space-time warping rather than conventional motion, you can construct scenarios where you depart Earth, arrive at a distant star, and then return to Earth before you left, arriving in your own past. This isn't just science fiction speculation. Multiple physicists, including Alan Everett and Roman Buny, have published detailed analyses showing that certain warp drive spacetimes, if they existed, could be used to construct closed time-like curves, paths through space-time that loop back on themselves. You could literally attend your own birth, meet your younger self, and potentially create paradoxes like the famous grandfather paradox, where you prevent your own existence. Most physicists find this deeply troubling. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow prevent the formation of closed time-like curves, at least on macroscopic scales. Maybe quantum effects destabilize any configuration that would allow time travel. Maybe the exotic matter requirements become infinite exactly at the threshold where causality would be violated. We don't know for sure because we don't have a complete theory of quantum gravity. Some warp drive researchers argue that causality isn't necessarily violated if you're careful. If you only use warp drives for outbound trips and never try to arrange a return journey that arrives before departure, you avoid the paradoxes. Or perhaps the universe has boundary conditions that simply forbid the existence of closed time-like curves, regardless of what local physics might permit. Others take a more radical view. Maybe causality isn't as sacred as we think. Some interpretations of quantum mechanics already challenge our intuitive notions of cause and effect. Perhaps in a universe where warp drives exist, time travel is possible, but nature has mechanisms we don't yet understand that prevent paradoxes. Maybe the many worlds interpretation applies, and timeline-altering events create diverging branches rather than contradictions. These are deep, unresolved questions in fundamental physics. They remind us that warp drive research isn't just engineering or even just physics. It touches on the nature of reality, time, causality, and the structure of the universe itself. Now let's talk about what happens inside a warp bubble during faster-than-light travel. Even if we solve the exotic energy problem and manage to create a stable warp field, passengers inside would face extraordinary challenges. One issue is communication and observation. If you're inside a warp bubble traveling faster than light relative to the external universe, light from outside can't catch up to you. You're surrounded by a horizon. Looking forward, you'd see intense blue shifting of any light that does manage to enter the front of your bubble, with frequencies compressed into an increasingly narrow, intense forward beam. Looking backward, you'd see nothing, complete darkness, as no light from behind can catch up. Communication becomes nearly impossible. You can't see where you're going. You can't receive signals from your destination or your origin. You're effectively isolated from the external universe for the duration of your journey. There's also the question of particles and radiation. Space isn't truly empty. It's filled with cosmic rays, stray atoms of hydrogen and helium, photons from the cosmic microwave background, neutrinos streaming from the sun, and distant supernovae. What happens when your warp bubble plows through this interstellar medium at superluminal speeds? Some calculations suggest that particles accumulate at the leading edge of the warp bubble, unable to enter or exit. Over the course of a long journey, you might build up a shell of trapped high-energy particles at your bow shock. When you finally shut down the warp field and arrive at your destination, all that accumulated energy might be released catastrophically, like a bomb detonating in front of your ship. This is sometimes called the warp drive death ray problem. William Clark and his colleagues at the University of Sydney studied this in 2012. They calculated that a warp bubble traveling to a star just 42 light-years away and then decelerating would release a forward-directed blast of particles and radiation with energies high enough to sterilize planets in the destination system, vaporizing anything in the beam's path. Your arrival would announce itself by destroying your destination. Potential solutions involve creating shield configurations, additional layers of warped spacetime that deflect or dissipate the accumulated particles before you arrive. But these add complexity to an already impossibly complex system. Each new solution creates new problems. Despite all these challenges, the research continues because the payoff would be transformative beyond measure. If warp drives are possible, even if they're centuries or millennia beyond our current capabilities, they fundamentally change the human future. Without faster-than-light travel, our descendants might colonize the solar system, perhaps sending slow-generation ships to nearby stars over timescales of centuries, but the galaxy would remain largely inaccessible. The Milky Way contains between 100 billion and 400 billion stars. Even traveling at 99% of light speed, crossing the galaxy would take over 100,000 years. Building a true galactic civilization would be impossible. With warp drives, the galaxy opens. Journeys that would take millennia could happen in years, months, or even days depending on the performance of your drive. Trade, communication, cultural exchange, and cooperation across interstellar distances become possible. Humanity, or our transhuman descendants, could become a truly spacefaring civilization, not limited to one planet or one solar system, but spread across thousands of stars. This isn't just about exploration or resources, though those matter. It's about survival. Every civilization confined to one planet lives under existential threat. Asteroid impacts, supervolcano eruptions, nuclear wars, engineered pandemics, runaway climate change, any number of catastrophes could extinguish us. Multiplanet species are more resilient, but even spreading across our solar system only reduces risk. A nearby supernova or gamma-ray burst could still sterilize everything within dozens of light years. A truly robust civilization needs to be multistellar, distributed across many separate star systems so that no single catastrophe can destroy it. Warp drives make that possible within reasonable timescales. There's also the question of contact with other intelligences. The Fermi paradox asks, if the universe is vast and ancient, where are all the aliens? If life and intelligence are common, shouldn't we see evidence of technological civilizations everywhere? Many solutions to the Fermi paradox depend on the impossibility or impracticality of interstellar travel. Maybe intelligent life exists but never leaves its home system because the distances are just too vast. Maybe every civilization concludes that interstellar colonization isn't worth the cost and effort. But if warp drives are possible, this explanation weakens. A sufficiently advanced civilization wouldn't be trapped by distance. If we're alone in the galaxy, or if technological civilizations are extraordinarily rare, the reason must be something other than travel limitations. Alternatively, maybe other civilizations have warp drives, and they're already here, just not interacting with us in ways we recognize. This veers into speculation about UFOs and alien visitation, topics that deserve scientific scrutiny but are often clouded by sensationalism and poor evidence. Still, if warp drives are physically possible, we should at least consider the possibility that someone else has already figured them out. Let me take a moment to place all of this in the broader context of physics and our evolving understanding of the universe. Every major revolution in physics has expanded what we thought was possible while constraining what we thought we knew. Newton's laws seem to describe a clockwork universe, predictable and deterministic, until quantum mechanics revealed that at small scales, reality is probabilistic, uncertain, and fundamentally weird. We thought space and time were absolute universal stages on which events played out, until Einstein showed that they're flexible, relative, and woven together into space-time. We thought the universe was static and eternal until Hubble's observations revealed it's expanding, that it had a beginning, and that its ultimate fate is still uncertain. We thought matter and energy came in a few familiar forms until cosmological observations forced us to accept that 95% of the universe consists of dark matter and dark energy, substances and effects we've detected only through their gravitational influence and that we barely understand. Each revelation was initially met with skepticism, then reluctant acceptance, then integration into a new, larger framework. The history of science teaches humility. What seems impossible today might be routine tomorrow. What seems crazy now might be obvious in hindsight. Warp drives occupy that uncertain territory between impossible and merely incredibly difficult. The mathematics works, the physics doesn't forbid them, though it makes them extremely challenging. Whether they transition from theoretical curiosity to engineering project depends on questions we can't yet answer. One of the most profound aspects of warp drive research is what it reveals about the structure of general relativity itself. Einstein's field equations, published in their complete form in November 1915, are deceptively simple-looking. They can be written compactly as G equals 8 pi t, where G is the Einstein tensor describing spacetime curvature, and T is the stress-energy tensor describing matter and energy distribution. But this elegant equation conceals extraordinary complexity. The Einstein tensor involves second derivatives of the metric, the mathematical object that describes distances and angles in space-time. When you write everything out explicitly, you get a system of 10 coupled, non-linear, partial differential equations. Non-linear means that solutions don't simply add up. You can't take two solutions and combine them to get a third. This makes finding exact solutions extremely difficult. In over a century since Einstein's breakthrough, physicists have discovered perhaps a few hundred exact solutions to his equations. The most famous include the Schwarzschild solution, describing non-rotating black holes, the Kerr solution for rotating black holes, the Friedmann-Lemaitre-Robertson-Walker solutions describing cosmology, and the gravitational wave solutions that LIGO detected. Each exact solution is precious because it gives us a window into what general relativity permits. When Alcubierre discovered his warp drive solution in 1994, he added a new window: faster than light travel without locally exceeding the speed of light, achieved through spacetime geometry rather than motion through space. The subsequent decades of refinements, from Van den Broek's modified geometry to Notario's alternative formulation to Rodal's irrotational design, represent humanity mapping out a new continent within the landscape of possible spacetimes. We're discovering which configurations minimize exotic energy, which are stable, which preserve causality, and which might actually be achievable. This is how physics progresses in the theoretical realm. You don't start by building the thing. You start by understanding what's mathematically possible. Then you investigate what's physically realizable. Then you eventually develop technology to implement it. Maxwell's equations describing electromagnetism were published in 1865. Radio technology followed in the 1890s. Television came in the 1920s. Radar in the 1930s. Microwaves, cell phones, Wi-Fi, and the entire telecommunications infrastructure of modern civilization all emerged from those same equations over more than a century. Perhaps warp drives will follow a similar trajectory. The mathematics exists now. Physical understanding is developing. Engineering implementation might take centuries, but the foundation is being laid today. Let me address another crucial aspect that's often overlooked in popular discussions: the control problem. Even if you could generate the exotic matter or energy needed for a warp drive, how would you control it? How do you turn it on and off? How do you steer? How do you accelerate smoothly rather than lurching chaotically through space-time? Consider the challenge of initiation. You're sitting on a planet or space station surrounded by normal flat space-time. You want to create a warp bubble around your spacecraft. This means dramatically warping space-time in your immediate vicinity, compressing space in front and expanding it behind. But creating that distortion requires distributing exotic matter or energy in a very specific geometric pattern around your ship. How do you do that? You can't just throw exotic matter in the general direction and hope it lands in the right configuration. You need precision placement of the energy distribution, probably to tolerances far beyond anything we can currently achieve. Some researchers have proposed using powerful electromagnetic fields or focused gravitational waves to sculpt the space-time geometry. Others suggest using multiple synchronized energy sources arranged around the ship, each contributing to the overall warp field pattern. But these are just conceptual sketches, not engineering blueprints. Then there's the question of dynamics during the journey. Space isn't uniform. You'll encounter variations in the gravitational field as you pass stars, planets, and other massive objects. You'll experience different densities of interstellar medium. Your warp bubble will need to adapt continuously to maintain stability. This is analogous to flying an aircraft through turbulent air. The plane doesn't just passively follow a ballistic trajectory, it constantly adjusts control surfaces, thrust, and orientation to maintain stable flight. A warp drive would need analogous control systems, sensing the local space-time environment and adjusting the warp field parameters thousands or millions of times per second to maintain the bubble's integrity. The computational requirements would be staggering. You'd need to solve Einstein's field equations in real time, accounting for the external gravitational environment, the distribution of matter inside and around your bubble, and the exotic energy configuration that maintains the warp. This might require quantum computers, artificial intelligence far beyond current capabilities, or entirely new forms of computation we haven't yet invented. Navigation presents its own challenges. Inside a superluminal warp bubble, you can't receive GPS signals or observe navigation stars. You'd need inertial navigation, tracking your acceleration and orientation to calculate your position, but even this becomes problematic when you're warping space-time itself. Your accelerometers and gyroscopes measure local space-time geometry, but that's exactly what you're manipulating. You might need to navigate based on gravitational mapping, detecting the large-scale distribution of matter in the galaxy and using that to infer your position. Or perhaps you'd place navigation beacons throughout space, specialized transmitters that can somehow communicate with warp bubbles despite the light speed barrier. Each solution creates new technical requirements. There's also the profound question of how you safely test such a technology. You can't build a warp drive prototype and just fire it up near Earth. If something goes wrong, the consequences could be catastrophic. An uncontrolled warp field might create gravitational distortions that damage or destroy nearby objects. The radiation release when the field collapses might sterilize everything nearby. A runaway warp bubble might not stop, carrying its contents on an uncontrolled journey into deep space or into a star or planet. You'd need to conduct tests far from any inhabited worlds, probably beyond the solar system entirely. But that creates a paradox. You need a working interstellar propulsion system to get to a safe test location for your interstellar propulsion system. Perhaps early tests would use smaller-scale warp fields, just enough to demonstrate the principle without risking uncontrolled superluminal travel. Or maybe initial experiments would focus on creating microscopic warp bubbles in particle accelerators, looking for the characteristic signatures without actually moving anything. Some researchers have proposed using laboratory-scale analogues of warp drive physics. Since 2010, several groups have studied acoustic black holes in fluids, arrangements where flowing water creates conditions analogous to a black hole event horizon for sound waves. Sound waves trying to propagate upstream against a flow faster than the sound speed get trapped, unable to escape, mathematically similar to light unable to escape a black hole. Could we create similar analogues for warp drives? Perhaps in flowing fluids, in carefully engineered metamaterials that manipulate electromagnetic waves in unusual ways, or in Bose-Einstein condensates where quantum effects create exotic effective spacetime geometries. These analogues wouldn't actually warp spacetime or enable faster-than-light travel, but they might let us study the control dynamics, stability properties, and energy flows in systems with mathematically similar behavior. The economic implications of warp drive technology would be transformative in ways difficult to overstate. Throughout human history, transportation breakthroughs have reshuffled economic and political power. Nations that mastered seafaring dominated global trade. Railroads opened continents and created industrial powerhouses. Aviation shrank the world and enabled modern globalization. Warp drives would be the ultimate transportation revolution, making interstellar distances economically traversable. Resources that currently exist only in our solar system, rare elements, asteroids rich in platinum group metals, the helium-3 in gas giant atmospheres, would become accessible throughout nearby star systems. Economic competition would shift from national to interstellar scales. The first civilization to develop working warp drives would have an enormous advantage, at least initially. They could explore, survey, and potentially claim resources across hundreds of star systems while others remain bound to their home worlds. This creates interesting strategic dynamics. Would knowledge of warp drive physics be hoarded as a state secret or shared openly? Would development be an international collaborative effort like CERN or the International Space Station, or a competitive race like the original space race? There's also the question of who gets to use such technology. If warp drives are incredibly expensive to build and operate, requiring resources available only to nations or megacorporations, they'd be accessible only to elites. Interstellar travel might become the ultimate luxury, creating a class divide between those who can afford to explore the galaxy and those confined to their home planet or system. Alternatively, if warp technology becomes mature and widely available, it could democratize space exploration. Individuals or small groups might own their own warp-capable craft, traveling between stars as easily as we now fly between continents. The social organization of a galaxy-spanning civilization with accessible warp travel would look radically different from one where the technology remains expensive and restricted. Consider the political implications. How do you govern across interstellar distances, even with warp drives? If a journey between Earth and a colony 40 light-years away takes weeks or months, you can have meaningful back-and-forth communication and maintain unified governance. But if colonies are spread across thousands of light-years, even warp-speed communication delays might be measured in years. Would a galactic civilization be a unified government, a federation of independent systems, or something entirely new? Science fiction has explored these possibilities extensively, from Star Trek's United Federation of Planets to Isaac Asimov's Galactic Empire to more anarchic arrangements in works by authors like Iain M. Banks or Alastair Reynolds. The reality would likely depend heavily on the specific capabilities of warp technology. Can you create stable wormholes for instantaneous communication, even if travel takes time? Can you build relay networks that speed information transfer, or are civilizations fundamentally limited by light-speed communication regardless of travel capabilities? These are the kinds of mind-bending questions we explore on this channel, the intersection of cutting-edge physics, future technology, and what it all means for humanity. If you're fascinated by these cosmic puzzles, hit that subscribe button right now. Trust me, you don't want to miss what's coming next. Let's also consider the cultural and philosophical implications. Humanity's self-conception has repeatedly changed as our view of the cosmos expanded. We thought Earth was the center of the universe until Copernicus and Galileo. We thought the Milky Way was the entire universe until the 1920s, when Edwin Hubble proved the existence of other galaxies. We thought our solar system was probably unique until the 1990s, when we began discovering thousands of exoplanets. Each shift was humbling and expanding simultaneously. We became smaller in the cosmic scheme, but the universe became larger and more wondrous. Warp drives would enable the next shift, from a species that knows intellectually that the universe is vast to one that can actually explore that vastness, moving among the stars rather than just observing them from afar. This might fundamentally alter how we think about our place in the cosmos. Philosophers have long debated humanity's cosmic significance. Are we a random accident, a brief flicker of consciousness in an indifferent universe? Are we cosmically important, perhaps the only intelligence for thousands of light years? Are we one among countless intelligent species, unremarkable in the grand scheme? The answers might depend on what we find when we can finally travel to other stars. If we discover life is common, perhaps even intelligent life, it would suggest the universe is teeming with consciousness, that mind is a natural and frequent outcome of cosmic evolution. If we find sterile worlds everywhere, it would suggest we're extraordinarily rare, perhaps alone, with corresponding responsibilities as potential stewards of life in the galaxy. Either discovery would be profound, either would reshape philosophy, religion, ethics, and our sense of meaning and purpose. And we can't make those discoveries, we can't actually know what's out there until we develop the capability to go and look. Warp drives are the technology that would enable that great exploration. There's also a spiritual or existential dimension that's worth acknowledging. Humans are explorers by nature. We've crossed oceans, climbed mountains, ventured to the poles, and walked on the moon, often at great risk and with little immediate practical benefit. We explore because we're curious, because the unknown calls to us, because there's something deeply human about pushing boundaries and seeing what lies beyond the horizon. For thousands of years, there was always a new horizon, new continents, uncharted islands, unexplored regions of the ocean depths. But in the 20th century, Earth became fully mapped. There are no undiscovered continents, no blank spaces on the map. The frontier closed, at least on our home planet. Space offers a new frontier, vaster than anything in human history. But the solar system, while interesting, is ultimately limited. A few dozen significant bodies, some scientific outposts, maybe some mining operations and colonies. The true frontier, the virtually unlimited expanse that could engage human curiosity and wanderlust for millions of years, is the galaxy and beyond. Warp drives are the key that unlocks that frontier. Without them, the stars remain forever distant, visible but unreachable, beautiful but isolated points of light. With them, each star becomes a potential destination, each planetary system a new world to explore. The psychological and cultural impact of that shift would be immense. Some critics argue that this is escapism, that we should focus on fixing Earth's problems rather than dreaming of the stars. There's validity to this concern. We do need to address climate change, poverty, conflict, and the many challenges facing our civilization. Running away to other planets doesn't solve those problems, but the dichotomy is false. We don't have to choose between improving Earth and exploring space. The technologies needed for long-duration space travel, closed-loop life support, sustainable energy, efficient resource use, are exactly the technologies we need to build a sustainable civilization on Earth. The perspective gained from seeing Earth from space, the overview effect reported by astronauts, often increases environmental awareness and concern for our planet's fragility. Moreover, keeping all of humanity's eggs in one planetary basket is risky. Working to preserve Earth and spreading to other worlds are complementary strategies for ensuring humanity's long-term survival and flourishing. Now let's examine some of the most recent theoretical breakthroughs that are shaping the current frontier of warp drive research. These developments, emerging primarily in the last 2 years, represent a maturation of the field from speculative ideas to increasingly rigorous physics. In late 2025, a research group led by physicists at the University of Göttingen published an analysis examining what they called the thermodynamic consistency of warp drive spacetimes. This might sound esoteric, but it addresses a fundamental question. Do warp drives respect the laws of thermodynamics? Thermodynamics, the study of heat, energy, and entropy, provides some of the most ironclad laws in physics. The first law states that energy is conserved. You can't create or destroy it, only transform it. The second law states that entropy, roughly speaking the disorder or randomness of a system, always increases in closed systems. The third law addresses behavior near absolute zero temperature. These laws have withstood every test for over a century and a half. They govern everything from steam engines to black holes, from chemical reactions to the ultimate fate of the universe. Any proposed technology that violates thermodynamics is almost certainly impossible, regardless of what other physics might suggest. The Göttingen team investigated whether warp bubbles, as they move through space and interact with matter and radiation, conserve energy and respect entropy constraints. Their analysis revealed something subtle. Certain warp drive configurations that appear mathematically valid might violate thermodynamic consistency when you account for interactions with quantum fields. Here's why this matters. Empty space isn't truly empty. Quantum field theory tells us that what we call vacuum is actually seething with virtual particles, quantum fluctuations that appear and disappear on timescales so brief they don't violate energy conservation thanks to Heisenberg's uncertainty principle. These fluctuations are real. They create measurable effects like the Casimir force and contribute to vacuum energy. When a warp bubble moves through this quantum vacuum, it disturbs these fluctuations. The rapidly changing spacetime geometry affects how virtual particles behave, potentially creating real particles in a process called the dynamical Casimir effect. This particle creation costs energy, which must come from somewhere, presumably from the warp drive's energy source. But the calculations showed something concerning. For certain warp drive configurations moving at high superluminal speeds, The energy required to account for particle creation from vacuum fluctuations exceeds what you'd expect. The discrepancy suggests either that energy isn't being conserved properly in these solutions, which would make them unphysical, or that there are additional energy sources or sinks we haven't accounted for. The team concluded that many proposed warp drive geometries need significant revision to ensure thermodynamic consistency. This doesn't mean warp drives are impossible, but it does mean we can't just focus on the geometric aspects and ignore how those geometries interact with quantum fields and thermodynamics. The physics all has to fit together consistently. This connects to another cutting-edge area of research, the quantum field theory of moving boundaries and horizons. When you have surfaces or boundaries moving at relativistic or superluminal speeds through quantum fields, complex effects emerge. Researchers at institutions including the University of Nottingham and the Max Planck Institute have been studying what happens when mirrors or boundaries accelerate rapidly in vacuum. They've found that accelerating boundaries can create particles, extracting energy from the vacuum in ways that seem to violate energy conservation at first glance, but actually don't when you account for the energy input required to accelerate the boundary. These studies have direct relevance to warp drives because the boundary of a warp bubble is effectively a rapidly moving discontinuity in spacetime. As the bubble moves, this boundary sweeps through space, potentially triggering particle creation and radiation. Some calculations suggest that a warp bubble might emit a form of Hawking radiation, similar to what black holes are theorized to produce. Black holes create radiation through a quantum process at their event horizon, where virtual particle pairs split, with one particle falling into the black hole while the other escapes as real radiation. The horizon of a warp bubble might do something similar. If this is true, it has several implications. First, it means warp drives would glow, emitting radiation characteristic of their speed and geometry. This could provide an observational signature for detecting natural or artificial warp bubbles. Second, this radiation represents energy loss, which would have to be compensated by the drive system. Third, if the radiation is intense enough, it might pose hazards to anything inside or near the warp bubble, a particularly fascinating paper from early 2026, authored by researchers including physicists from the Perimeter Institute and the University of Waterloo, explored the connection between warp drives and quantum entanglement. Entanglement is the phenomenon where quantum particles become correlated in ways that persist even when the particles are separated by large distances. Einstein famously called it spooky action at a distance. The researchers investigated what happens to entangled particles when one is inside a warp bubble and the other remains outside. Quantum entanglement is incredibly fragile. It's easily disrupted by environmental interactions, a process called decoherence. But entanglement also seems to transcend space in ways we don't fully understand. When you measure one entangled particle, you instantaneously affect the state of its partner, regardless of the distance between them. This seems to violate relativity's prohibition on faster-than-light information transfer, but it doesn't, because you can't use entanglement alone to send messages. The correlations only become apparent when you compare measurement results, and that comparison requires normal light-speed limited communication. Still, the nature of entanglement is deeply mysterious and possibly relevant to understanding space-time at fundamental levels. The team's calculations suggested that warp drive motion might create novel forms of quantum correlations, or alternatively might disrupt entanglement in characteristic ways. If true, this could provide another experimental signature. If we ever create even tiny warp bubbles in laboratory settings, we could test for their effects on entangled particles. This would be far easier than building a full-scale warp drive, but could still provide crucial evidence about whether the underlying physics is correct. There's also been fascinating work on alternative mathematical formulations of warp drives using different geometric approaches. Most warp drive research uses what's called the ADM formalism, a particular way of splitting space-time into space plus time, which makes it easier to understand how spatial geometry changes over time. But there are other mathematical frameworks for describing general relativity. One particularly promising approach uses conformal transformations, mathematical operations that change distances in space-time while preserving angles. Some researchers have found that certain warp drive solutions can be understood as conformal transformations of simpler spacetimes. This is interesting because conformal transformations often preserve important physical properties while changing others. If you can map a complicated warp drive solution onto a simpler, better understood spacetime through conformal transformation, you inherit knowledge about the simpler spacetime. Questions about stability, causality, and energy conditions in the complicated solution might have answers that you can read off from the simpler version. Researchers at the University of Lisbon and the University of Cape Town have been exploring these ideas, publishing papers that recast warp drive physics in terms of conformal geometry. They've found that some of the exotic energy requirements that look impossible in standard formulations might be more tractable when viewed through conformal approaches. This doesn't magically solve the negative energy problem, but it opens new mathematical avenues for attacking it. Sometimes in physics, a problem that seems intractable in one mathematical language becomes solvable when you translate it into a different framework. Maxwell originally formulated electromagnetism using mechanical models with wheels and gears. The modern vector and tensor formulations are equivalent but far more powerful and elegant. Perhaps warp drives need a similar reformulation. Another active research area involves numerical simulations of warp bubble dynamics. Until recently, most warp drive research was purely analytical, solving Einstein's equations by hand with paper and pencil, or at most with symbolic computation software. But some questions are too complicated for analytical solutions. You need to simulate the system numerically, calculating how it evolves step by step on powerful computers. Numerical relativity, the art of solving Einstein's equations on computers, came of age in the early 2000s with successful simulations of merging black holes. These simulations require sophisticated techniques to handle the nonlinear, coupled nature of the equations and to avoid numerical instabilities that can cause calculations to crash or give nonsense results. Since around 2023, several groups have adapted numerical relativity codes to simulate warp bubbles. These simulations can address questions that analytics can't easily answer. What happens when a warp bubble accelerates from rest? How does it interact with gravitational waves passing through the region? What happens if two warp bubbles collide? The results have been eye-opening. Some warp configurations that look stable in static analysis turn out to develop instabilities when you simulate their formation or acceleration. Others show unexpected resilience, maintaining coherence even when disturbed. The simulations reveal that the transition moments, turning the drive on, changing speed, turning it off, are especially challenging. The space-time geometry has to change dramatically, and doing so smoothly without creating dangerous singularities or regions of infinite curvature requires very careful control of the energy distribution. One simulation from a team at the University of Texas at Austin showed that if you try to accelerate a warp bubble too quickly, the bubble can fragment, breaking into multiple smaller regions of warped spacetime that drift apart. This is analogous to how a water droplet can break apart if you accelerate it too forcefully. the implications for drive control are clear. You need smooth, gradual changes in the warp field strength, not sudden jumps. Another simulation from researchers at the Albert Einstein Institute in Germany explored collisions between warp bubbles. What happens if two warp-capable ships pass each other going in opposite directions at high superluminal speeds? The results were complex and depended sensitively on the details of the bubble geometries and their relative speeds. In some cases, the bubbles passed through each other with minimal interaction, each preserving its integrity. In other cases, the interaction created gravitational wave bursts and temporary disruptions to both bubbles. In the most extreme cases, the bubbles could merge or catastrophically disrupt each other, potentially releasing enormous amounts of energy. These findings suggest that traffic control in a galaxy with warp-capable civilizations would be critically important. You couldn't have ships traveling on arbitrary trajectories at arbitrary speeds. You'd need designated routes, speed limits, and coordination systems to prevent catastrophic collisions. Imagine air traffic control, but for interstellar space with faster-than-light vehicles. The organizational challenges are daunting. Let me now turn to a topic that often gets less attention, but is equally important: materials science for warp drives. Even if we solve the exotic energy problem and figure out the control systems, we still need to build physical structures that can withstand the extreme conditions inside and around a warp bubble. The stresses on a spacecraft inside a warp bubble would be extraordinary. The ship sits at the boundary between regions of contracted and expanded spacetime. Tidal forces, gravitational gradients across the ship's length could be immense. The ship's structure would need to withstand these forces without deforming or fracturing. Current materials, even the strongest alloys and composites, might not be sufficient. We might need materials with properties we can barely imagine: incredible tensile strength combined with flexibility, resistance to radiation at levels far beyond anything in our current environment, thermal management capabilities to handle extreme temperature gradients. Some researchers have proposed using carbon nanotubes or graphene-based materials which have extraordinary strength-to-weight ratios. Others suggest programmable matter or smart materials that can dynamically adjust their properties in response to changing conditions. The most speculative proposals involve exotic matter, not just for the warp field, but for the ship's structure itself, materials with negative mass or negative pressure that could counteract the stresses imposed by the warped space-time. We're also beginning to understand that shielding would be absolutely critical. Even if the warp bubble itself protects you from relativistic particle collisions, you'd still be exposed to intense radiation from various sources. Hawking-like radiation from the bubble boundary, accumulated particles at the bubble's leading edge, cosmic rays blue-shifted to extreme energies. Effective shielding against such radiation might require meters-thick barriers of water, metal, or specialized absorbing materials. Alternatively, you might use active shielding, powerful magnetic fields that deflect charged particles, or layered warp field configurations that create buffer zones between the ship and the most extreme radiation environments. The engineering challenges extend to power systems as well. Even with Rodal's optimized warp drive geometry, you're looking at power requirements far beyond anything humanity has built. The International Space Station generates about 100 kilowatts from its solar panels. A fusion reactor, if we ever build working ones, might produce gigawatts. A warp drive needs terawatts or more. Sustained for potentially weeks or months of continuous operation, current nuclear fission reactors are far too weak and bulky. Fusion reactors, if we achieve them, might be a starting point, but would likely still fall short. Antimatter reactions offer the theoretical energy density, but storing and controlling antimatter safely in the quantities needed is a separate, enormous challenge. One mistake, and you have an explosion that makes nuclear weapons look like firecrackers. Some designs propose beamed power, where energy is generated elsewhere and transmitted to the ship via laser or microwave beams. This works fine near your home star, but becomes impractical as you travel light years away. You'd need relay stations, enormous infrastructure investments, or onboard generation capabilities. Perhaps the solution involves extracting energy from the warp field itself. The warped space-time might have accessible energy gradients that could be tapped. This would be analogous to extracting energy from a black hole's rotation via the Penrose process. You'd essentially be pulling energy from space-time geometry, a fascinating concept, but one that requires understanding of physics we don't yet possess. There's also the question of navigation computers and artificial intelligence. Controlling a warp drive in real time, adjusting field parameters thousands of times per second, navigating around gravitational hazards, managing energy flows, all while isolated from external communication, demands computational capabilities far beyond current systems. You'd likely need artificial general intelligence, machines that can understand, learn, and adapt as flexibly as humans, but at vastly higher speeds. The AI would need to understand general relativity, quantum field theory, and engineering at expert levels, making split-second decisions that might mean the difference between successful flight and catastrophic failure. This raises interesting questions about the relationship between humans and AI in a warp-capable civilization. Would humans still pilot ships, or would we become passengers trusting AI to handle the incomprehensibly complex physics? Would we merge with AI through brain-computer interfaces, augmenting our capabilities to match the demands of warp navigation? Or would we send AI alone, exploring the galaxy while humans remain safely behind? Let's now explore one of the most intriguing recent developments in warp drive physics: the connection between warp drives and the quantum structure of space-time itself. This represents a shift from viewing warp drives purely as solutions to Einstein's classical equations toward understanding how they might emerge from deeper quantum theories of gravity. The central challenge in theoretical physics today is reconciling general relativity, which describes gravity and space-time as smooth, continuous geometric structures, with quantum mechanics, which describes matter and energy as fundamentally discrete and probabilistic. These two pillars of modern physics are spectacularly successful in their respective domains, but appear incompatible when you try to combine them at extremely small scales. Around the Planck length of about 10 to the negative 35 meters, quantum fluctuations of spacetime itself should become important. Spacetime might not be smooth at these scales, but rather foamy, discrete, or structured in ways we don't yet understand. Several approaches attempt to describe quantum gravity: string theory, loop quantum gravity, causal set theory, and others. None are yet experimentally confirmed. Here's where it gets interesting for warp drives. Some researchers have begun investigating whether warp bubble configurations might be more natural or achievable in quantum gravity theories than in classical general relativity. The idea is that what looks like exotic matter with negative energy in the classical description might actually be a manifestation of quantum gravitational effects. In 2025, a theoretical group including physicists from the University of Cambridge and the University of Waterloo published a paper exploring warp drives in the context of loop quantum gravity, one of the leading approaches to quantum gravity. Loop quantum gravity suggests that space is not infinitely divisible, but instead has a discrete structure at the Planck scale, woven from tiny loops of gravitational field. The researchers found that in this framework, certain configurations that would require negative energy in classical general relativity might instead be achievable through specific arrangements of quantum geometric states. The negative energy density wouldn't come from exotic matter, but from the quantum geometry of space itself, regions where the discrete structure of space-time creates effective negative energy when viewed from a classical perspective. This is still highly speculative and depends on unproven assumptions about quantum gravity. But it's conceptually fascinating. It suggests that warp drives might not require exotic matter that we need to discover or create. Instead, they might require mastery of quantum spacetime engineering, manipulating the fundamental structure of space at Planck scales. If true, this shifts the challenge from how do we find or make exotic matter to how do we control quantum gravitational degrees of freedom. This might actually be more achievable in the long run, though it would require technological capabilities far beyond anything we currently possess. You'd need to manipulate space-time at scales 20 orders of magnitude smaller than an atomic nucleus, requiring energy concentrations and precision that seem impossible with current physics. But impossible with current physics is not the same as fundamentally impossible. There might be clever techniques we haven't discovered yet, perhaps involving quantum entanglement, quantum computing, or other quantum information tools that allow macroscopic control over quantum gravitational states. A related line of research investigates whether warp drives might exist as solitons in certain quantum field theories. Solitons are stable, localized waves that maintain their shape as they propagate. They appear in many physical systems, from water waves to fiber optics to certain quantum fields. In some extended theories of gravity, theories that add extra terms to Einstein's equations or extra fields beyond the metric, soliton solutions exist that resemble warp bubbles. These solitons propagate through the quantum vacuum, carrying energy and momentum in localized packets. They're stable against small perturbations and can move at various speeds, including potentially superluminal ones. Physicists at institutions including Imperial College London and the University of Copenhagen have explored these ideas, asking whether our universe might already contain the fields necessary to support warp solitons. Perhaps dark energy, the mysterious component driving the universe's accelerated expansion, is actually a field that admits warp drive solutions. Perhaps what we interpret as dark energy's negative pressure is a manifestation of the same physics that could enable warp drives. This is admittedly quite speculative, but it illustrates how warp drive research connects to fundamental questions about the universe's composition and structure. Understanding warp drives isn't just engineering, it's probing the deepest levels of physical reality. Another fascinating development involves the holographic principle and its implications for warp drives. The holographic principle, inspired by black hole thermodynamics and developed extensively in string theory, suggests that all the information in a volume of space can be encoded on the boundary of that region. The three-dimensional reality we experience might, in some sense, be a projection of information stored on a two-dimensional surface. This sounds like science fiction, but it's taken seriously by leading theoretical physicists because it resolves certain paradoxes in quantum gravity and appears naturally in string theory through the AD-S-CFT correspondence, a mathematical duality between gravitational theories and quantum field theories. Several researchers have begun investigating what warp drives look like from a holographic perspective. If our three-dimensional spacetime is encoded on a boundary, what does warping spacetime mean in terms of the boundary description? How does a warp bubble's superluminal motion manifest in the holographic encoding? Preliminary work suggests that warp bubbles in the bulk spacetime correspond to particular excitations or configurations on the holographic boundary. These boundary configurations might have energy properties that differ from the bulk interpretation. What looks like negative energy density in the bulk might correspond to a perfectly normal, positive energy configuration on the boundary. If this is correct, it might provide a resolution to the exotic matter problem. The negative energy isn't really negative. It's just an artifact of viewing a holographic system from the bulk perspective. Creating a warp bubble wouldn't require exotic matter, but rather engineering the right boundary state, which then manifests as warped spacetime in the bulk. Again, this is highly theoretical and depends on the holographic principle being correct, which is still debated. But it represents creative thinking about how to reconcile warp drives with fundamental physics. It shows that researchers are taking seriously the possibility that warp drives might be achievable through avenues we haven't fully explored yet. Let me now discuss some practical considerations for a hypothetical future civilization attempting to build warp drives. Assuming the physics eventually works out, what would the development timeline and requirements look like? First, you'd need a massive scientific infrastructure. The physics research alone would require investments comparable to or exceeding current major scientific projects like the Large Hadron Collider or the International Space Station. You'd need teams of theoretical physicists, experimental physicists, engineers, computer scientists, and specialists in numerous fields working collaboratively for decades. The experimental program would progress through stages. Initial experiments might focus on creating tiny distortions in space-time using powerful lasers or particle beams, looking for any evidence that space-time can be warped in controllable ways. Success at this level wouldn't prove warp drives are possible, but it would validate that we can manipulate space-time beyond what natural gravitational fields provide. Next would come attempts to create microscopic warp bubbles, perhaps enclosing a single atom or molecule. These wouldn't achieve superluminal speeds, but they demonstrate that the geometric configuration of a warp bubble can be stabilized, even briefly. Diagnostics would be extraordinarily challenging. You'd need to measure space-time geometry on microscopic scales with incredible precision, probably using interferometry techniques far beyond current capabilities. Success at the microscopic scale would lead to progressively larger demonstrations, centimeter-scale bubbles, meter-scale bubbles, eventually bubbles large enough to enclose a small spacecraft. Each scale-up would present new challenges. Larger bubbles require more energy and might have different stability properties. The engineering tolerances become more demanding as systems grow. Parallel to the physics experiments, you'd need to develop the engineering infrastructure, energy generation, and storage systems capable of handling the enormous power requirements, materials that can withstand the stresses, control systems that can manage the complex dynamics, life support systems for eventual crewed missions. You'd also need to establish a testing infrastructure in space, probably well beyond Earth orbit. Testing warp drives near inhabited planets is simply too dangerous. You'd need remote facilities, perhaps in the outer solar system or even in interstellar space, where a catastrophic failure wouldn't endanger anyone. The timeline for all this is highly uncertain. With a massive, well-funded global effort, perhaps we could go from current theoretical research to the first tiny space-time distortions in a decade or two. From there to microscopic warp bubbles might take another few decades. From microscopic to macroscopic, another half-century. From demonstration to practical interstellar capability, perhaps another century beyond that. So we're looking at a minimum timeline of perhaps 200 to 300 years from now to functional warp drive technology. And that's assuming everything goes well, that the physics works out, and that civilization maintains the focus and resources to pursue this goal continuously. More realistic estimates might be 500 to 1,000 years or longer. This seems discouraging, but consider that we're contemplating technology that would enable travel to the stars, fundamentally transforming humanity's future. It's worth pursuing, even if the payoff is centuries away. Many of our greatest achievements, from cathedrals to scientific knowledge to social institutions, were built over generations, with the understanding that completion might be far in the future. There's also the question of alternative approaches. Warp drives are one possible path to interstellar travel, but not the only one. Other possibilities include generation ships, vessels that travel at sublight speeds for centuries, with populations living and reproducing during the voyage. There are suspended animation approaches, where passengers sleep through long journeys. There are proposals for laser-pushed light sails, achieving high fractions of light speed through external power. Each approach has advantages and disadvantages. Generation ships require no exotic physics, but commit populations to centuries in space with all the associated risks. Suspended animation requires biological technologies we don't have. Light sails can only accelerate away from their power source, making deceleration at the destination challenging. Warp drives, if achievable, would be superior to all these alternatives in terms of trip time and flexibility, but they're also the most demanding in terms of physics and engineering. A mature civilization might pursue multiple approaches simultaneously, using conventional technologies for nearer destinations while developing warp capability for more distant exploration. There's also the possibility of discovering shortcuts we haven't imagined yet. The history of technology is full of surprises. Heavier-than-air flight was achieved through different principles than early theorists anticipated. Nuclear energy came from splitting atoms, not chemical reactions. The Internet emerged from Cold War military communications research. Perhaps warp drives will be enabled by a discovery we haven't made yet. A new principle of physics that makes what now seems impossible much more tractable. Or perhaps an entirely different approach to faster-than-light travel will emerge from future physics, something we can't currently conceive because we lack the necessary conceptual framework. This is one reason why fundamental research is so important. When you investigate the frontiers of knowledge, you never know what you'll find. Quantum mechanics was developed by physicists studying the glow of hot objects and the emission spectra of atoms. They weren't trying to develop semiconductors, lasers, or computers, but quantum mechanics enabled all of those and more. Relativity came from thinking about light and electromagnetism, not trying to design GPS satellites, but GPS depends crucially on relativistic corrections. Similarly, warp drive research, even if it never produces functional warp drives, will certainly advance our understanding of spacetime, gravity, quantum fields, and exotic states of matter and energy. Those insights will have applications we can't predict. The journey is valuable, even if the specific destination turns out to be unreachable. Let me address one more important consideration: the ethics of warp drive development and use. This might seem premature when we're centuries from having the technology, but thinking through ethical implications early can guide research directions and policy development. First, there's the question of environmental impact. Warp bubbles moving through space would disturb the local environment, creating gravitational waves, potentially emitting radiation, and possibly affecting anything in their path. If warp drives become common, these effects could accumulate. Would frequent warp travel damage the structure of space-time? Could it affect the development of young planetary systems or disturb interstellar clouds where stars are forming? We need to understand these impacts before deploying the technology at scale. This requires modeling and eventually experimental data. Establishing environmental standards for warp travel would be crucial, just as we now have environmental standards for aviation, shipping, and industrial processes. Second, there's the question of access and equity. Advanced technology often creates or exacerbates inequality. If warp drives are expensive and accessible only to wealthy nations or individuals, they could create a new form of colonialism, with advanced civilizations exploiting resources in star systems while excluding less advanced peoples. Alternatively, if warp technology is shared openly as a common heritage of humanity, it could be a unifying force, enabling cooperative exploration and development of the galaxy. The choice between these outcomes depends on decisions made during development, on intellectual property regimes, on international agreements, and on our values as a civilization. Third, there's the question of contact with other intelligences. If life exists elsewhere in the galaxy, warp-capable humanity would inevitably encounter it eventually. How should we approach such contact? Do we have a right to visit other star systems? What if they're inhabited? What ethical frameworks govern interaction with alien civilizations, particularly if they're less technologically advanced than us? Science fiction has explored these questions extensively, from Star Trek's prime directive of non-interference to more interventionist approaches. Real policy would need to be developed thoughtfully, probably informed by disciplines including ethics, anthropology, sociology, and astrobiology, not just physics and engineering. Now, if you think warp drives will solve all our interstellar problems, think again. The reality is far more challenging than you might expect. Click on the video appearing on your screen right now to discover the hard truth about traveling between the stars that nobody talks about. Trust me, this will completely change how you see space travel.